Welcome to today's paper reading. Today's paper is titled, Geospecific View Generation Geometry Context-Aware High-Resolution Ground View Inference from Satellite Views. This paper, to be published in ECCV 2024, is authored by Ningli Su and Rongjun from The Ohio State University. The abstract highlights the challenge of predicting realistic ground views from satellite imagery in urban scenes, due to significant view gaps between satellite and ground view images. To address this, the authors propose a novel pipeline that generates geospecific views by respecting weak geometry and texture from multi-view satellite images. Unlike existing methods, this approach directly predicts ground view images at geolocation using comprehensive satellite image information, resulting in ground-level images with a resolution boost of 10 times or more. Key innovations include a novel building refinement method to reduce geometric distortions and a geospecific prior that prompts distribution learning of diffusion models to respect image samples closer to the geolocation of the predicted images. This pipeline is the first to generate close-to-real and geospecific ground views based solely on satellite images. The cross-view synthesis problem involves predicting ground view images from satellite images, which can significantly benefit applications like 3D realistic gaming and city-scale scene synthesis. However, this task faces several challenges. Firstly, the difference in viewing angles makes the transformation highly sensitive to noise. Secondly, the resolution disparity between satellite images, 0.3 m/pixel, and street view images, 3 cm per pixel, complicates the extraction of useful information. Additionally, color distortions due to cloud reflections further complicate the synthesis process. Existing methods often lack ground fidelity and photorealism, making the development of a more accurate approach necessary. Figure 1 showcases examples of our synthesized geospecific views. Unlike other methods that rely on semantics, our approach uses ground view satellite texture, which provides high-frequency structural and color information. The predicted results exhibit photorealistic quality and accurately reflect the number of stories of the garage, marked as orange rectangles. In cross-view synthesis, the goal is to generate ground views from top-down satellite images. This task faces significant challenges due to the large viewport and domain differences. Existing methods address these challenges using conditional GNs and geometry-based transformations. Conditional image generation involves learning a mapping between source conditions and target image domains. Common conditions include text descriptions, broken images, and street view semantics. Conditional GNs and diffusion models are widely used in this field, with diffusion models showing better adaptability to various image domains. Cross-view geolocalization focuses on estimating the location and orientation of ground view images using satellite images. Early approaches treated this as an image retrieval problem, while recent methods leverage geometry guidance and Siamese networks for more accurate localization. The pipeline for ground view panorama synthesis is divided into 4 main stages: the top-down view stage, projection stage, ground view stage, and texture-guided generation stage. The primary goal is to achieve geometrically accurate projection of satellite textures to the ground view, focusing on enhancing the synthesis of ground view images by capturing subtle details of building facades. Techniques such as 2D-3D-2D projection and RPC projection are employed to transform satellite textures, while a diffusion model is used in the texture-guided generation stage to iteratively synthesize ground view images from random noise maps. Figure 2 provides an overview of our pipeline designed to predict ground view panorama images using satellite images. The pipeline is divided into 4 stages: the top-down view stage, projection stage, ground view stage, and texture-guided generation stage. In the top-down view and projection stage, satellite textures are projected to refine 3D geometry, and then back to ground view 2D space. The ground view stage uses the ground view satellite texture and corresponding high-frequency layout information as conditions. Finally, in the texture-guided generation stage, a diffusion model is employed, conditioning on ground view satellite textures, high-frequency information, and a geospecific prior. Figure 3 illustrates the texture-friendly geometry refinement process. This process begins with the original height map as its input. It then proceeds to estimate the building footprint, which is crucial for accurately representing the structures in the scene. Following this, boundary regularization is applied to produce a refined height map, ensuring that the geometry is smooth and precise. This refinement is essential for maintaining the quality of textures projected onto building facades, which are nearly perpendicular to the satellite viewing direction. The process employs a 2D unit to classify each pixel as either part of a building or non-building region, thereby enhancing the accuracy of the building footprint detection. Figure 4 presents examples of satellite textures before and after undergoing our transformation-friendly geometry refinement process. Initially, the building boundaries are rectified into a series of polygons to ensure smooth edges. Non-building regions are flattened onto a fitted plane while preserving the original configuration of building pixels. Following refinement, a 2D/3D texture projection is performed, and panoramic projection is applied to derive the ground view satellite textures. This method demonstrates exceptional results across various building types, as illustrated in the figure. Figure 5 illustrates the three conditions utilized for cross-view synthesis. The first condition, semantics, is a common approach in existing works, 2:2241. Our method introduces satellite textures as a second condition, which provides high frequency and color information, enhancing the detail of building facade layouts, including the shapes and locations of windows and doors. The third condition is an edge map, which further refines the structural details of the building facades. Figure 6 showcases examples of synthesized results where different geospecific priors are applied to the same query condition. This figure highlights how varying geospecific information can influence the generated images, demonstrating the model's ability to incorporate regional attributes such as specific vegetation types or building features. The consistent query condition ensures a controlled comparison, allowing for the clear observation of how each geospecific prior affects the final output, thereby illustrating the effectiveness of the model and capturing and reflecting geographical nuances. Figure 7 showcases examples from our cross-view dataset based in Jacksonville, Florida, USA. This dataset features well-aligned pairs of ground view satellite RGB images and their corresponding ground truth images. Additionally, it includes top-view RGB images and height maps. These elements are crucial for the detailed analysis and processing of geospecific views, providing a comprehensive resource for various applications in satellite imagery and geographic information systems. Table 1 presents a quantitative evaluation of the quality of synthesized images, comparing our method with four baseline methods: SAT2 ground, SAT2 density, cross-MLP, and PANOGN. The evaluation metrics include low-level metrics such as PSNR and SSIM, edge-level metrics like IE, semantic-level metrics including IB, IG, and IS, and perceptual-level metrics such as LPIPS, FID, and DreamSim. Our method demonstrates superior performance across these metrics, particularly in PSNR, SSIM, and LPIPS, indicating higher image quality and perceptual similarity to ground truth images. In this section, we discuss the baseline methods chosen for comparison, including cross-MLP, PANOGN, SAT2 ground, and SAT2 density. These methods represent direct synthesis and geometry-guided approaches. For evaluating the quality of synthesized results, we employ a combination of low-level, edge-level, semantic-level, and perceptual-level metrics. Low-level metrics such as PSNR and SSIM assess differences at the pixel or local patch level. Edge-level metrics, like the IOU of edge maps, measure similarity at the edge level. Semantic-level metrics, including IOU for building, ground, and sky labels, evaluate the recognition of synthesized objects by pre-trained semantic segmentation models. Perceptual-level metrics, such as FID, LPIPS, and DreamSim, provide a measure of the perceptual quality of the synthesized images. These metrics are crucial for a comprehensive evaluation of the synthesis methods. Figure 8 showcases a qualitative comparison of our synthesis method against SAT2 ground, SAT2 density, cross-MLP, and PANOGN. The figure highlights that our method produces more photorealistic images with fewer artifacts, particularly in building facades. This improvement is evident in the edge-level performance, where our method achieves a significant enhancement over the baseline methods. The synthesis results demonstrate a closer resemblance to ground truth images, indicating superior perceptual quality. Figure 9 presents a qualitative ablation study, showcasing the visual comparison of synthesized images generated by our methods under different configurations. This figure highlights the impact of geospecific priors and texture conditions on the quality and accuracy of the synthesized images. By comparing configurations without these elements, we can observe the significant improvements they bring to the synthesis process, ensuring more realistic and detailed outputs. Table 2 presents the results of a quantitative ablation study focusing on the proposed geospecific priors and the ground view satellite texture condition, which is referred to as RGB. This study is conducted under the same settings as those used for Figure 9. The table likely provides numerical data that demonstrates the impact of these geospecific priors and the texture condition on the performance or accuracy of the model, offering insights into their effectiveness and necessity within the model's architecture. Table 3 presents the quantitative results demonstrating the potential improvement of baseline methods when incorporating our ground view satellite texture conditions over traditional semantics. The metrics LPIPS, FID, and DreamSim are used to evaluate the performance. For LPIPS, the texture conditions show a significant reduction from 0.509 to 0.449 compared to semantics. Similarly, FID improves from 170.8 to 71.04, and DreamSim from 0.434 to 0.315. These results highlight the importance of texture conditions in providing richer details and less ambiguous mapping relations, as qualitatively illustrated in Figure 9. Figure 10 illustrates the training efficiency comparison between our method with and without the geospecific prior. Notably, at the early stage of 2000 training steps, the inclusion of the geospecific prior significantly enhances the method's ability to synthesize results that closely resemble the ground truth. This demonstrates the effectiveness of the geospecific prior in accelerating the training process and improving the quality of synthesized outputs. Figure 11 illustrates the limitations of our method due to the inherent randomness of the diffusion model. The synthesis results, marked as orange rectangles, exhibit inconsistencies with their neighboring views. This inconsistency is evident in the color and facade layouts of buildings synthesized at adjacent locations. The randomness in the diffusion model prevents the results from strictly adhering to the input conditions, highlighting the need for explicit cross-location or view consistency constraints in future work. In this paper, the authors propose a novel pipeline for predicting ground view images from multi-view satellite images. The predicted views are geospecific, meaning they are consistent with both the geometry and textural information derived from the satellite views, with a resolution enhancement of at least 10 times. The authors introduce a geometry refinement module to refine the satellite 3D geometry, which minimizes texture distortions on building facades and significantly improves the transfer of structural information. Additionally, a geospecific prior is used to control the learned distributions of the diffusion model, ensuring the predicted views respect local street view styles and accelerating training convergence. Experimental results show that this method outperforms existing baselines and can predict high-resolution, authentic ground views using only multi-view satellite images. This research is partially supported by the Intelligence Advanced Research Projects Activity, IRPA, through the Department of Interior/Interior Business Center, DOI/IBC, with contract number 140D0423C0075. The U.S. government is authorized to reproduce and distribute reprints for governmental purposes, regardless of any copyright annotations. Additionally, the research is supported by the Office of Naval Research with award numbers N00014201241 and N00014231260. The authors would like to acknowledge Shi Lu for his valuable discussions during the course of this work. It is important to note that the views and conclusions expressed in this work are those of the authors and do not necessarily represent the official policies or endorsements of IRPA, DOI/IBC, or the U.S. government. Thank you for watching.